lead us in prayer, begin us in prayer for today.
Father, Son, Holy Spirit, amen. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done, on earth as it is in heaven. Give us this day our daily bread. Forgive us our trespasses, as we forgive those who trespass against us. Lead us not into temptation, but deliver us from evil. Amen.
Very good. Thank you. Thank you very much. All right, so let's see. All right, let's see. We have Mr. Busman coming in, but the last time it wasn't necessarily him. Let's see if he comes in. All right, gentlemen, so I'll say hello to him. All right, so who else did I need? So Chris, your homework. Luke, I spoke to you. Alex, I spoke to you. Mick's not here. Joseph, I saw yours. No Zion. Okay, let's see who else. And TJ, so we don't have TJ with us yet, right? Okay, boys. So number one thing, so first, after our prayer, our mustard seed today is pretty quick, very quick one. All right, so today's mustard seed. If you sow thistles, you will not reap corn. Sow good seeds, good mustard seeds. All right, gentlemen, sow good seeds in your brains. Let's go. We all ready? Josh, you all bundled up, ready to go? All right, so give me 1 second here. Okay, so before we begin. All right, so number one thing, priority, is that I'm going to give you guys a quiz on Monday. And the way that I'm going to do my quiz is live. So when you log in, I'm going to share my screen with you, which will have your quiz on it, or I'm going to send you an email with a Google document. So is there anybody here who has not used any of the Google Forms or anything yet? So it comes across almost like a survey. So if I do that, are we good? And then the reason I want to do that, number one, is so that you have me available to answer questions as you are doing it. So obviously, yes, it will be, you know, open notes, open book. I don't mind that at all, but I don't want you emailing and text each other. So I want to give it to you live. You will have to have your video camera on. So Jacob Shively, can I just have you say hello? Oh, okay, just want to make sure that was you. And let's see, Joelle's just joining us. Chris, that's you. We already saw your video, right? Okay. Oh, here comes Zion. Okay.
I was Martin Weaver.
Zion, is that you?
Yeah.
Okay, just needed your voice there. All right, very good, gentlemen. Okay, so number one. So make sure we have everybody. Zion, any homework for me today?
Yeah. All you have to do is read, right?
No, there was a worksheet that went with it. Did you happen to get that done?
I was caught up on other things.
All right, well, make sure you check Blackbaud. It's on Blackbaud. So we're going to go over it today. All right, gentlemen. So we're going to go over that today. I'm going to mute you guys as we get started here. If you have a question, as always, you are welcome to unmute yourself. And let me just scroll down here. Okay. Okay. So most important thing, quiz. Monday. It's going to be on momentum, which is chapter 6. Okay. So that's going to be on momentum, chapter 6. So as I go over this work today, make sure you pause and ask questions if you have any as we go over this. All right. So definitely want to go over your homework. Number one.
Ms. Weaver?
Yes.
Where's the homework? I'm in black by. Is it momentum worksheet or something?
Conservation of momentum worksheet. Yes,
Yeah.
that's
All
it.
right, thanks.
You're
We
welcome.
about to go to that
Can I
right
use the
now.
bathroom?
Yes. We're okay. So is that Josh?
Cause that was Freddie.
Freddie, yes, okay. Okay, everybody, let's go over your homework. So what we did last time, just a quick review. Let me pin my video here. All right, so quick review so that it makes more sense. When I was going over your notes and what I looked at for homework, what I didn't see is enough equations and pictures drawn and everything. Do not lose your good problem solving skills. So your problem solving skills are to draw a picture, list what you know, then write an equation, then you solve. So all of you that turned in the second half of the homework, the second page with just an answer on it, that's not efficient to give you full credit as we go forward. Full credit, I want a picture. What do you know? What do you want to know? An equation, right? And then you can start plugging in your information. And you'll see today how that really helps in solving the problems. So conservation of momentum is what we concentrated on last time. And that's what we're working on right now. And that is, in the absence of an outside force, the momentum of a system that is closed is constant. So the way we wrote that mathematically is to say momentum of 1 plus momentum of 2, if I only have 2 objects, before an event takes place is equal to the momentum after the event. So remember, this symbol of a prime was afterwards. So I wrote this equation for you last time, but we didn't necessarily use it very much. We talked some about it. Momentum, okay? Luke Seeley, how do I find momentum of an object? What's the equation to find momentum?
I forgot.
Anybody? What do I do to find momentum?
You multiply mass times velocity.
Very good, Chris. Excellent. Momentum. So what I can substitute here is momentum of number 1 is going to be the mass of number 1 times velocity of number 1 plus mass of number 2, velocity of number 2. And that's going to be equal mass number 1, velocity 1 after plus mass number 2, velocity of number 2 after. This is the equation we're going to use like crazy today, okay? So this is going to be the important stuff we're going to see today. So what I would like to do first is actually start off with this, and then I think if we really understand this, going back and answering some of the questions might make more sense. So I'm going to begin right away actually with one of the problems. So I'm going to do my screen share here with your homework. Okay, so this was your homework. I'm going to skip these first couple questions and scroll down here to question number 6. Okay, and this is how I would like to see this worked out. A 2-kilogram blob of putty moving at 3 meters per second slams into a 2-kilogram blob of putty that is at rest. Show how the speed of the 2 stuck together immediately after colliding is 1 meter per second. Okay, so hopefully you guys can all see that. What I'm going to do is I'm going to draw a picture. If you don't have your homework sheet near you, write down that equation, because then I'm going to get rid of the work and show you only this. So you basically have object number 1, object number 2, right? One object is at rest, so our velocity is 0, but it has a mass of 2 kilograms, right? They both have a mass of 2 kilograms. This one is moving with a speed of 3 meters per second, but also has a mass of 2 kilograms. So this is number 5, okay? When you are taking a look at this, all right, make sure you recognize that that's what you want to do. what are the two objects, object one, object two, what do I know about them? What are they doing? And then something takes place. They stick together. They collided. So that means now I have object one, object two, right? Their velocity afterwards, we're going to call v1 prime. We don't know what it is. We're just going to call it v prime. But since they're stuck together, v2 prime equals v prime also. They equal the same thing. You can let it equal x, whatever you want. They both still have the same mass, 2 kilograms, 2 kilograms, right? So that's what I want everybody to do in solving these problems. What's happening before, what's happening after, okay? So everybody has that problem. I'm going to go back and stop the share. Okay.
Miss Riceweaver,
Yes.
can this be in the docs as well?
What do you mean? In what?
The homework.
It
Can we
should be
put
in class documents and assignments. I thought you already found it.
Yeah, but like, can I put it into like a docs?
Sure. It is in a Word document.
Oh, okay.
You can save it however you want. Yep. All right, so I want to just focus on my screen, and I want all of you guys to be paying attention and writing what we see up here on the whiteboard. Okay, so this is number 5. All right, so this is true, what we started off class with. The momentum of blob number 1 plus the momentum of blob number 2 before they stick together must equal the momentum of blob number 1 after plus the momentum of blob number 2 after. Since they stuck together, their two velocities are equal to one another. Okay, since they are stuck together there. So what we want to do here is now write this equation like that. M1 V1 plus M2 V2 is equal to M1 V1 after plus M2 V2 after. Okay. So the ultimate question is, what is V prime? This is what we really want to know. So our question is, how fast are they going after they collide and stick together? So I'm going to plug in my numbers of what I know, and I'm going to solve for this. I see that these two are going to be equal to the same thing. So what I'm going to plug in here is 2 kilograms times 3 meters per second, right? Plus 2 kilograms times 0 meters per second. And that equals 2 kilograms times V prime, because that's what V1 prime is afterwards, plus 2 kilograms times V prime. So I have 2 of the same thing over here. On the left side, we have 6 plus 0, right? Kilogram meter per second plus 0 kilogram meters per second equals. Over here, these two can just add. So that's going to give me 4 times V prime because they're exactly the same thing. So I would say 4 kilograms times V prime. Okay. So it looks complicated because of all of our units and the primes and the subscripts. Just know that everything means something. And when you go back to your picture, it should make sense of what those mean. So here, 6 plus 0, right? Easy, 6 kilogram meters per second equals 4 kilograms times V prime. running out of space here. So I would divide both sides by 4 kilograms. And the kilograms cancel along with the 4, right? So 6 divided by 4 is how much? 1.5. So my answer, 1.5. The kilogram cancels here, and I end up with just units of meters per second equals V prime. And that's what you were asked to do in that problem. So a lot of you said the 1.5 came from 3 divided by 2. Like you made up a reason to get 1.5. But what we was asking is prove when these two stick together, that's going to be your speed afterwards. Know that it is less than the original object's speed, and it's actually half as much. The original speed was 3. This is half as much because the two stuck together, giving you twice the mass afterwards, moving with only 1 velocity because they're stuck together. So I'm going to give you a moment to write that down. We didn't do too much with the numbers last class. We did more conceptual thinking. So that's how in this equation we can put in our numbers. All right, thumbs up. Everybody has it all written down. Freddie, you good? Henry, you good? Miles is good. Austin, you got it? All right, anybody need more time writing this? Everybody good? Josh, are you still writing or you have a question? You're good? Okay. All right, so now what I want you to do is I want you to work on problem number 6. Let's take a look at now problem number 6. I'm going to pull that back up for you while it's fresh in your head. Let's take a look at problem number 6. Okay, Betty has a mass of 40 kilograms. She's standing on ice, which means there's no friction, and the importance of that is that there's no outside force. Just like my carts that I was showing you last class, there is no friction. So you can imagine she's standing there, the doll comes up and jumps in her arms and she catches them. How fast are they going to be moving afterwards? So it's very similar. 2 objects stick together and move. They would slide. So the question is, how fast will they be moving after? Okay. So I want everybody to draw me a picture of what that looks like. List what you know, what you want to know, and write your equation. And let's see if we can get the right answer.
Did I go to the bathroom, Ms. Rothenweaver?
After you draw a picture
Of question 6.
of question 6, I may ask you guys to show me your work. So I want everybody, not question 6, number 7, I'm sorry. I'm sorry, I messed up. This work was number 6, not number 5. Sorry about that. And now I want everybody to look at number 7. And I'm going to ask you to hold up your papers for me so I know you're doing your work.
We just draw you a picture.
Draw me a picture of what that might look like. What does that scenario look like?
We doing number 7, right?
Correct. All right, Freddie, you got it? Do you have an answer? Okay, I like the picture. Now what are we gonna do?
I can't draw.
Okay, I'm gonna stop the screen share. Is everybody okay with that? All right. Kendall, you have a picture for me?
I mean, I can't draw, so here, I guess.
Okay, do you have to draw a person? Not necessarily, right? You can draw 2 circles. It's actually the exact same scenario that we had in number 6. 2 objects, right? Then they stick together afterwards. So what is this going to look like? All right, it looks exactly the same as what we did. All right, so let's take a look at this again. You basically have 2 objects, right? So you can draw them just like that. They don't have to be people. You have this person. What was Betty doing? Her mass is, how much is Betty's mass?
40 kilograms.
Nick, how much is Betty's mass?
40.
40 kilograms. How fast is Betty moving, Nick?
She's at rest.
She's at rest. So my velocity would be?
0.
0. How much momentum does she have?
0.
0, because she's not moving. Her dog comes and jumps on her. So if I keep it like this, the dog's going to be going that way, right? So in this problem, we would say the mass of the dog is 15 kilograms, but its velocity is to the left. So I would say negative, how much? Austin, what's the velocity of the dog? I think you're muted. Here, I'm going to unmute you. Okay, Austin, how much is the velocity of the dog?
I didn't calculate it. I
What?
know it's negative.
It's
didn't
negative because she's
calculate.
going backwards. Anybody remember what it was? Henry?
Negative 3 meters per second.
Very good. Henry, I'm glad you got your voice in there. Negative 3
I fixed it.
meters per second. Is everybody good with this? Okay, yes, Josh, you're good to go. All right, so if I go back to this, now they stick together afterwards, right? Their masses don't change. So her mass is still 40 kilograms. The dog's mass is still 15 kilograms. But now her velocity is the same as the dog's velocity, and we're going to call it V prime. So our question is, how fast do they move afterwards? Because of conservation of momentum, we know they must move to the left. So one thing we do know is they must be going to the left. So there's our, what we know, a quick picture. Now we say momentum of Betty plus the momentum of her dog before he jumps on her must equal the momentum of Betty plus the momentum of her dog after. And that's what the prime means. Momentum is m1 v1 vector quantity plus mv of object number 2 must equal m1 v1 afterwards, that's the prime symbol, plus m of the dog afterwards, right? So again, we plug in our numbers. All right, I'm going to pause. And I want everybody to get me an answer, and you're going to hold that up to the screen. Plug in your numbers and get me an answer. Okay. Nolan, did you get an answer yet? All right, if you got an answer, hold up your paper to the screen. Let me do a quick look. Nick, you got an answer? Let me see your work. Henry, that looks good, but I like units. Left out your units. Chris, you getting it? I can't quite see your answer, but it looks good. Does it make sense? Good. Ethan, you got anything? Nick, okay. Oh, what are the rest of you all doing? Oh, there we go, Ethan. Okay. Joelle, we doing any work there? You have any work? You have any work to show me?
Oh, it's finished.
Joseph Kelly, did you get an answer?
No, ma'am. I'm kind of confused on it.
Oh, what are you confused? Read, that looks good. Joseph, where are you stuck? Joseph, any question?
Oh, I figured it out. I didn't put like the negative sign.
Okay, so what's your answer?
For -7, I got -3 meters per second.
What do you mean by for -7?
I mean, for question 7, I got -3 meters per second.
No, that was the original speed of the dog.
Well, I thought,
So I'm solving for V prime here. What am I going to do to get V prime by itself? I'm going to divide by 55 on both sides. All right, gentlemen, even online, it is important that you're not just watching, but you are participating. So, all right, so we're going to divide by 55. So -45 divided by 55 will give us our V prime. So -45 divided by 55. Henry, what was your answer?
It was -0.81.
And what'd you decide on the units?
I said, what is it? Kilograms.
Okay, that's a good thought, but it is a velocity. So what should be our units? of
Oh,
its
so then it
velocity?
would be meters per second.
Very good, meters per second. And Henry, that is correct. So afterwards, when she catches her dog, she's going to be going in the same direction as the dog, but with much less speed because the two stick together and now you have more mass, right? Okay, so we're going to come back if we have time to do numbers 8 and 9. But first I want to demonstrate this for you with our carts. So we're going to go back. Does anybody have any questions? Okay, we need to make sure you can solve these. This is going to be on your quiz on Monday. So I'd like to practice some more of that, but let me demonstrate what we saw here. So if I get back to my carts, let me go back to my, if you guys have me in that speaker view. All right, so here's our carts, right, that we were using last time. Same way, there we go. All right, so what's going on here? This is a case where they're going to stick together, right? So problem number 6, they both had the same mass. This one's coming together, they stick, they move off together with the same velocity, but much, much slower than the original, right? So I'm going to come together, they stick, and they move off with a slower velocity than the original. In problem number 6, that was half as much velocity because these have twice the amount of mass once they stick together, okay? At rest, moving, right, comes in, they get stuck together, all right? The dog one, the dog's coming in here. The lady is at rest. She has more mass. So I'm going to put more mass on top of my cart to represent Betty. Here's Betty, here's her dog. She's at rest, has no momentum. So that's this side of the equation. So the system is all of this together. The dog's coming in, it's very light, but it's moving fast, right? And it's going to come in and stick, and look how slow they move, but in the direction of the dog, right? So even though she has more mass, it's not like this goes in and bounces off. They continue to move forward, but very slow. So the dog was moving with a 3 meters per second. Together afterwards, they were moving with even less than half as much because we had so much more mass at the end. So one thing I hope you guys have been getting all year is what we're seeing physically is being proven in our math that we're taking a look at here. Don't let these letters and symbols scare you. They explain exactly what we saw, okay? All right, does anybody have any questions on those 2 problems? Okay, those are perfect scenarios of what we're seeing there, okay? All right, so let's go back to the homework and answer some things. So problem or question number 1, or let's see, maybe we should work backwards. Yeah, let's work backwards from problem number 6, right? So let's go back to the shared screen. All right, if I scroll up here. And the reason I want to work backwards is I give you a little break from the math, but in number 5, if the equally mass of, well, I guess we need to do number 4 first. Railroad car A rolls at a certain speed and makes a perfectly elastic collision with car B of the same mass. After the collision, car A is observed to be at rest. How does the speed of car B compare with the initial speed of car A? So in this case, if I go back and you're taking a look at my whiteboard here, right? So if we go back up to the whiteboard, this was the very first scenario that I showed you. These 2 things have the same mass. This is what we did on Monday, right? This one's at rest. This one comes in and collides with it. So mathematically, what does that look like on our whiteboard? We now have this one having velocity, but they have the same mass, right? We'll go back to the same scenario here. All right, they do not stick together, right? So what happens here is this one's at rest. This one has a velocity. Elastic collision means they're allowed to bounce off of one another. They're not going to stick. But if you remember, when this one comes in, hits that one, it pretty much stops. This one moves off with the same velocity, right? So they simply transfer momentum. So the answer to number, let's go back to, I'm going to type it in so you guys can write down exactly what we want to say here. The answer to number 4, railroad car rolls at a certain speed and makes a perfectly elastic collision with B. What's going to happen here? If I go in and I type into here, let's see. Right? So car B moves with the same speed as car A. And then what happened? Car A, Okay, now that's the result because car A stops, right? So for conservation of momentum, if I had momentum of NV before, I must have momentum of NV after. So looking at number 5, if the equally massive cars in the preceding question stick together, how does their speed after the collision compare to the initial speed of car A? So what's going to happen now when they stick together? Okay, so I'm going to go back to this. Same masses, right? This one's coming in, they're going to stick together. This is what we saw in problem number 6, right? They come in, they stick, they move with a slower speed and exactly half as much speed because I now have doubled my mass moving forward. Okay? So this momentum, let's say, is 10. When it comes in, I must have a momentum of 10 afterwards, but that 10 is the result of both of these moving together. Okay? So each one of them would have 5 and 5, adding up to be 10. The 10 that was there before and the 10 that was there after. All right, let's answer that on our sheet. Sorry, guys. All right, I just want to type this in so you guys have it in your notes. So the answer to number 5, right? Okay, they will half the speed of the initial. Okay. Now, again, the reason that is, this is because mass is doubled when they stick together. Okay. So since the mass doubles, they will stick together. Okay, let's look at number 3. So I'm working backwards just because we're working off the math that we were doing. Cannonball is fired, momentum is conserved when they're just at rest. Would momentum be conserved for the system if the momentum were not a vector quantity? And the answer here is, what do we think there? Would momentum be conserved if it was not a vector quantity? And the answer is, I'm going to type it for you. No. You need to have a final momentum of 0 after the firing of the cannon. Okay. The momentum before the cannon was fired is 0, right? So the momentum after has to be 0. The only way you get 0 is if you add a positive value and a negative value. All year, the only way we got a negative value is if it was in a different direction. So that's what's meant by being a vector quantity. We need that to have direction. Okay, quick thumbs up. Does everybody have that written down? Good on that? All right, let me demonstrate this for you. Okay, I like this one. And many of you may be hunters. Who are my hunters out there? Henry, do you go hunting? Yep. All right. How about just target shooting? Austin,
Not
you go target shooting, you hit the clay pigeons? All right. What happens when you shoot that rifle? What happens to you?
It kicks back.
Kicks back. Okay, why? Is exactly what's being discussed in this problem on number 3. Okay, what's neat about these carts, this spring that's in here, is I can lock it. So then I can press it and it gets fired. So it shoots out. Okay, so I can mimic this. If I put these two things together, okay, so I set that up. All right. Right now, the momentum of my system, Josh used, is how much? What is the momentum of my entire system here? You're muted.
I didn't hear you. My mom called me. I had to go. She told me something.
Well, you're back. So here you go. 2 cards
Momentum of the
sitting
whole-
at rest. What's the momentum of my system?
0.
0, because they're not moving, right?
Yeah.
So if I cause there to be a force between them, like an explosion, like would happen in the firing of the cannonball or rifle when you're clay pigeon shooting, or rifle when you're shooting, right? So if right now it's 0 and then they're going to push off of one another, what's going to have to happen? So this is what question number 3 is asking.
There's
So
gonna have
what
to be an
happens
internal force.
if I hit this and they, right? Whoops, wait. Right? One goes to the left and one goes to the right. Now, why is that? In terms of momentum, let's go back to our math over here. So if we go back to our board, so I'll try to write this down here at the bottom. If they are both at rest to begin with, I have velocity of 0, velocity of 0. So my momentum before is going to be 0, right? Only way I get 0 on this side is if the bullet or the cannonball has to go off like that, then it has a value. Let's say it has a value of 500 kilogram meters per second. So if this is to move, if this is my cannonball and it's going to go flying across the field, right, then it has momentum because it's moving. The only way I get 500 to become 0 is to add a negative value to it. So I must add negative 500 kilograms so that I get 0 equals 0. Momentum before equals momentum after. Now, what happens to you is you're very big. The cannon is very big. So if I were to do this again, right, and they fire, so is everybody watching this? This is a good demonstration. All right, now if I let this go and they fire, it still has a momentum of 0 before the firing. I must still have momentum of 0 after the firing. So if I release this one goes very fast. This one went pretty slow, right? So watch that again. I'm going to start it over there just so it has more room. Whoop, I caused it to move. Hold on. Get it on the track correctly. Sometimes they work perfect. All right. It's causing me to, there we go. Goes off very fast, this one's slow. This is you holding the rifle. You have much more mass. So for your momentum to equal this one, you don't need a lot of velocity. This one's momentum is very high because it's shooting out very, very fast. So, and its mass is very, very small. All right, we have just a few minutes left. Let me finish up these last few questions. So we are not going to get to problems 8 and 9. So please make sure that is going to be your homework, is to go back and make sure you finish 8 and 9, and I will post the solutions to those 2 problems. All right, so looking at number 1, can you produce, okay? Can you produce a net impulse on an automobile if you sit inside and push on the dashboard? And the answer here is no. These forces are internal. Just like the explosion of what I just showed you. That would be considered an internal force. Okay, so they do not cause an impulse. Impulse is only caused by external. What does it mean to say, or any quantity, that momentum is conserved? So conservation means that the quantity or the magnitude is the same before and after. It never changes. Okay? So the quantity is the same before and after. Okay, so Chris, I know you said you were understanding a little bit better. Do you mind stop my share there? How's everybody else doing? Making a little bit more sense now that we did that all together? So your homework is to please do numbers 8 and 9. I will post solutions to Blackbaud. You can check under the course documents for the answers to that. My suggestion would be you go back and do numbers 7 and 8, or 6 and 7 first, and review those because that's what we worked through, okay? Also on the quiz is the work that we did before break on momentum and impulse and everything. So you had a couple worksheets there as well. All of chapter 6. It'll be definitions, problems, answering questions, okay? Yes, Hunter, if you want to hold on for a second, I'll go back to number 2. Everybody else, if you don't have any questions, have a great D period class. I will see you on Monday. Have a good weekend. Okay, I'm going to pull that back up, Hunter. There you go.
What's up, Boston?